developed with the different class of partners. From academic side, we have 3 partners involved from France, which is University of Lille, the lead partner, TU Delft, and University of Portsmouth from UK. From the medical partners, we have involvement of 3 partners, which is Oncovet Clinical Research, which is veterinary clinical research, and the cancer center here in Lille, called Oscar Lambry, and NHS Portsmouth Hospital. We 2 other classes of partners are involved in the project, which are Urasanti, which is a cluster of life science and health from the north of France, and 2 private companies, one from France, which is Satnor, specializing in the industrialization of research prototype, and Demcom from the Netherlands, which is specialized in developing prototypes or devices for diagnosis of cancers in AMR environment. So in parallel to the partners, or the full partners, we have a set of observers. Without these observers, of course, our research activities will not reach the principal objectives. From France, we have the Hospital of Amiens, and Institute of Face in Faces. We have another cluster in medical sector in the south of UK, which is Wessex Academic Health Science, and we have also a set of enterprise where we receive a good support from them in terms of facilities to get in images, or facilities of equipment that we use them during our common development, such as Philips Medical and Electa from the Netherlands, and Eckers and Ziegler, MTT, Marvis, Noras, and KUKA from Germany. Good. So our main objective is to propose solutions for the diagnosis and treatment of localized cancer of prostate in bore under control of MRI by developing a mini-invasive solutions. Here you have a view of what it exists right now with the external radiation therapy, where we are using an MR Linac here. There is 2 versions of MR Linacs nowadays available in the market, one European and one American. And this is for external radiation therapy, and our objective is to go with the same principle, combining between MRI and automated treatment system, but for brachytherapy concept. So our integration follow this V diagram, where we started in 2018 with the simple requirement and technical specifications. That means we started from TRL6, and our objective by the end of September is to converge to TRL6 by making this, the testing of on-live animals. Here globally, our common environment of the CoBra project, where this afternoon we share with you all the demonstration through this platform. Thank you so much, John. And
thank you, Rushdie, for this nice introduction. Then I like to ask Sarah Wilby from Portsmouth University Hospital to share her presentation.
Oh, I will just share now. Hold on. Okay, can you see my screen?
Yeah, it's fine.
Great. Okay. So good afternoon. So I'm presenting on behalf of the collaborators of the CoBra project to give a little bit of a clinical introduction and clinical perspective to the project. So Roshni has already shown this slide, but just to point out that our project is coming to its concluding stages, so it ends in September of this year. And to reiterate the project aims, so primarily we are trying to improve the quality of both diagnosis and treatment of localized cancers by developing a new medical robot prototype, which will be used in MRI. And Roshni has already given us a nice introduction of the partners, so I won't go through those again. So the CoBra project in the first instance is focusing on prostate cancer, addressing both diagnostic biopsies and also therapeutic brachytherapy, which, as we know, is a type of radiotherapy. So both of these procedures offer the opportunity to replace the manual needle insertion, which is what we currently do clinically, with a robotic technique. And just before we discuss the potential benefits of replacing that manual with robotic, I'll give a few statistics relating to prostate cancer. So why prostate? Well, in 2020, the worldwide statistics showed that there were 1.4 million new cases of prostate cancer. It's the second most frequent cancer in males. There were 375,000 deaths, and it's the fifth leading cause of cancer mortality. It is also a technique that we have a lot of experience with, and we can understand the technique and see the benefits of potentially moving from manual to robotic. So to give you an overview of the current clinical situation for biopsies in the first instance. So for a prostate biopsy, we're sampling the prostate tissue, and you can see in this picture on the right here that we are extracting small cores of prostate tissue. They're around about 2 centimeters in length, but less than 1 millimeter in diameter. And those cores can be sent off to histopathology for diagnosis. In order to extract those cores, we can reach the prostate either transrectally, as you can see in this diagram on the left, or through the perineum, as you can see in the center image here. And this is actually quite a rapidly changing field, with different departments, different centres using different techniques. Some using a template, as you can see here, to guide the needles into position. Others using more of a freehand approach. Some using the transrectal, some transperineal, some using a general anaesthetic, and some using local anaesthetic. But the National Prostate Cancer Audit from December 2019 shows in this first graph here that the change from transrectal to transperineal has been quite rapid over the years, and almost exclusively everyone is now using the transperineal approach, at least within the NHS, but that's not necessarily the case globally. What we can see from the histogram on the right here is that the move from transrectal to transperineal has reduced the amount of sepsis. So that's shown by this navy blue bar here. So the transrectal approach on the left and then the transperineal approach here. And you can see that the sepsis in navy blue has reduced between the two. But you'll also notice that there's an increase in urinary retention. And the likely reason for that is to do with the number of samples that are taken. If you increase the number of samples taken, then you increase the risk of urinary retention. But we can't really reduce the number of samples taken unless we're really confident about where we're extracting those prostate cores from. Are we actually hitting the cancer? And in order to achieve that and be confident and therefore reduce the number of cores that we take, it's really important that we have good quality imaging and that we can target accurately. And so that's where the MRI comes in. At the moment, we're generally focusing on ultrasound, and it's very difficult, if not impossible, for the majority of lesions to see them on ultrasound. However, on MRI, as you can see from these images here, particularly if we benefit from multiparametric MRI, we can really feel much more confident in identifying where the lesions are that we need to target. So our current clinical practice is to bring the patients in for an MRI prior to their biopsy, and then use that MRI to contour the prostate and identify where the lesions are. In theatre, they'll then have a live ultrasound image, which we fuse with the MRI and transfer the contours across so that we can then target on the ultrasound just the lesions and not the whole of the prostate itself. So moving on from biopsy to brachytherapy, very, very similar setup, similar equipment. We only use transperineal approach, as you can see here. But the difference is that rather than extracting cores, we're inserting radioactive seeds, and that can either be a low dose rate, around about 50 to 100 seeds into the prostate. These are about the size of a grain of rice. Or if a higher dose rate technique is used, then a single source is moved in and out of different channels within the prostate, but to achieve a similar dose distribution. And ultimately, what we want to do is treat the prostate whilst avoiding organs at risk. This diagram in the top left, the central portion here is the urethra, and you can see that we've got these islands of hotter dose on either side, and we're managing to spare the dose to the urethra. So what's important about both of these techniques, whether it's biopsy or brachytherapy, is that they both share a need for precise treatment. So if we look at a biopsy, the lesions may only be around about a half cc in diameter, but they can be hidden in a prostate volume that's up to 120 cc. So that makes it very difficult to target unless you have good imaging and good targeting technology. And similarly with brachytherapy, there are very steep dose gradients in brachytherapy around the source. There's organs at risk close by that we need to avoid: the urethra, the bladder, the rectum. If the seeds aren't placed correctly within the prostate capsule, then they can migrate. So precision is important for both of these techniques. So what are the limitations of the current practice that we can possibly improve on with the CoBra project? We've spoken about there being insufficient information on the ultrasound alone and much clearer imaging, particularly for soft tissue and for lesions in MRI. We can fuse the two as we do currently, but there is a risk of misaligning both ultrasound and the MRI. There's a risk of misaligning the two. It's also additional imaging and additional time. It's very difficult to track deformations of the prostate gland during the procedure if you have two image sets that are registered together. We're limited in terms of accessing all parts of the prostate gland with the current technique of using straight needles and a template. And there are also obstructions which can cause more difficulties in accessing all of the prostate. So that could be caused by the pubic arch or the angle of the urethra, or sometimes calcifications within the prostate tissue. And lastly, we do get inter-operator variability in the quality of the targeting of the biopsy cores or the quality of the brachytherapy plan itself. So the CoBra project is proposing a number of solutions to resolve these problems, all of which are MR compatible. And they all stem from the robotic arm, which has been developed at the University of Lille. And then to attach onto that, we have an automatic seed loader, a biopsy module. TU Delft have developed steerable needles to avoid the issue of not being able to access all parts of the prostate. The University of Portsmouth have looked at needle path and seed planning. Centre Oscar Lambert have looked at dose calculation on MRI images directly. and the University of Lille have devised a bio-inspired phantom. So during this workshop, each of these separate topics will be discussed, and then I believe there's a demonstration at the end. So start with the steerable needles from TU Delft. I think John looks like he's ready to take over on that presentation, so I will hand over to him. Thank you very much and hope you enjoy the workshop.
Thank you very much, Sarah, for this very clear introduction in the medical needs and also the introduction of the partners. Still, I want to give the people the opportunity to ask questions if there are any for Sarah. Not at the moment. I can understand that people with a clinical background are well aware of all the clinical challenges. So thank you again, Sarah. That also gives you the opportunity to go to your clinical work, which is waiting.
Yes, apologies for that, but I'm going to leave you to it.
That's fine.
Thank you. Okay.
Thank you again. Well, Sarah was mainly introducing me. That's because my name was on the program, but of course everybody knows that Martijn was mostly doing the work. So I would like to ask Martijn, he's already sharing his screen, to present the developments that have been done by Delft University of Technology.
Thank you, John. So one remark, in clinical practice, we first always start with the biopsy, and then we continue with the therapy. But right now we do it the other way around. So I will start with the brachytherapy procedure or the module. In Delft University of Technology, we developed a steerable needle mechanism to optimize low dose rate prostate brachytherapy, which is normally performed, as Sarah already told, by using rigid needles. And if we look at the aims, we want to increase control of the needle trajectory and the end position during the insertion of the needle. And we want to enlarge the reach within an obstructed or an enlarged prostate to obtain a more homogeneous dose distribution. So we want to overcome interference of the pubic bone, which is laying in between the prostate and the perineum. And as you see, the ventral part of the prostate can be obstructed. So by using a steerable needle, we can overcome this issue. But we looked into literature and we couldn't find decisive numbers. So we set up our own study in collaboration with Portsmouth University Hospital. And we looked at the quantification of the pubic arch interference in patients with enlarged prostates above 50 or 60 cc, because normally these patients are not eligible for prostate brachytherapy based on their volume. And we looked at 20 data sets, and we found that 9 of those 20 patients had more than 10 millimeters of obstruction of the prostate due to the pubic arch, which could not be solved by using, for instance, manipulation of the rigid needles or placing the patient in a more extended lithotomy position. So that really asked for another solution. And we saw that we needed up to 50 millimeters of steering over an insertion depth of up to 100 millimeters. So this study really set the requirements for our needle, for needle steering. So a small recap about the design. It comprises of an outer catheter and an inner needle. And the inner needle contains 4 segments which are joined at the tip. And by pulling and pushing the proximal end of the needle, we can steer the distal tip of the needle inside the tissue of the patient. And in this way, the needle shaft will follow the orientation of the tip. and we can have active needle steering in multiple planes. So we can steer in all directions within the tissue. And if the catheter is placed, we remove the inner needle and we create a channel which can be used for stranded and loose seed delivery. We performed experiments and we saw that we can actually obtain lateral steering up to 50 millimeters, which therefore we can conclude that 16 of those 20 patients we included in our study can be treated by this steerable needle approach, and we therefore do not need prior hormonal therapy to downsize the prostate and make it more accessible for the needle. So in that way we avoid bothersome side effects for the patient. So over here we see the brachytherapy module. Over here we have 4 piezoelectric motors which are MR conditional, and by using these motors we can actuate the segments and we can allow for steering at the tip. We see that over here that there is a two-way port. One port is used for needle steering, and after the needle is placed in the right area of the prostate, we retract the inner needle and we created a channel for seed loading via the other port. And this brachytherapy module is mounted on the linear guide of the robot developed at the University of Lille. And with this module, we can target multiple areas in the prostate without the total retraction of the instrument from the tissue. So we performed some experiments at the facility of Philips in Best, and we placed the module. Oh, there is a movie as well. So we insert the needle. It's mounted on the robot guide. We will see this within an hour on the demonstration. Oh, the movie is not playing, right? Do you see it or?
It's not moving, Martijn. That
okay.
sometimes
Okay.
happens within Teams. My apologies for that.
Believe me, it is moving. We looked at the distortion within the MRI, and we saw that distortions mainly occurred at the distal tip, which is actually quite common. They will form a blue and ball void, but if we look at the distortions, it's still okay within the margins, and we can define this system as MR conditional. Over here, a setup. We developed a prostate phantom. So over here in red, we see the prostate, and there is some bone in between as well. And I have a small video after, but I hope it will work. Otherwise, I have to switch. Let me check. Do you see the? Yeah. Okay. So over here you see the video. So we inserted the needle into the phantom, which had a skin in between as well. And when the needle was inside the tissue, we steered it upwards to reach the ventral area of the prostate, which is obstructed by the pubic bone. And after placement, we withdraw the inner needle, as I told before, to create a channel for seed loading. So yeah, for the integration, so we can mount this module on the robotic guide, and with this steerable needle system, we are suitable, which is suitable for MR imaging. Yeah, it can be controlled and inserted by the developed robotic system, and the output will be suitable for experimental evaluation and for dissemination as well. So thank you. Nice,
Thank you.
nice picture of the group as well, which is actually quite old already.
Okay, thank you, Martijn. Yeah, it has been a while since we were all together.
Yeah, that's true.
Thank you again. Luckily that the video worked outside of the presentation. It's very clear. Are there any questions for Martijn? Not at the moment. And since we started a bit late, then I would like to move on to the next presentation from Professor Ashraf Labib of University of Portsmouth.
Okay, thank you very much, John. Welcome, and let me try to share my screen. Give me 1 second. Can you see my presentation?
It was just coming up. Now I see a great, yeah, it's there.
Yeah. So I'm Ashraf Labib. I'm on behalf of our team, Professor Dylan Jones, who I believe is with us. Dylan is with us as well. And Dr. Sina Feruzi, whose contract has finished with us. He used to be our research associate who helped us in developing the trajectory planning for the needle. So as was presented before, the overall, I think Professor Rojdi Marzuki showed the overall process between the different partners, and then Sarah as well. Our role really is to focus on this bit here, where we look at the trajectory planning and feed it into a software interface. And our input is coming from the calculations of the dose planning and the calculation. The formulation and the data structure used in the path planning and real-time path adaptation program. And this is what we are looking at, and to have an algorithm for needle trajectory in the context of robotic brachytherapy and biopsy. So we have here an assumption in our work is that the seed plan has been prepared and fed to the trajectory planning using the conventional seed planning, which Sarah shows through the grid. So we assume that this is coming for us, assuming that it was a straight needle. It has also been assumed that the operation of the seeds can change with respect to the original plan without violating the radiation field requirement. Obviously the advantage of the steerable needle is that it gives us flexibility. And what we try to do is to try to minimize the number of insertion and to obviously to avoid the organs and risk and so on. So this is an overall sort of flow of our integrated program. And as Martijn has showed that we have a needle design comprised of a straight needle, rigid cannula, and a pre-bent stylus that keeps its intended curvature once deployed inside the patient bodies. And the algorithm assume a circular curvature for the styles. So having the MRI image, what we would like to do in additional to avoiding the organ at risk is also to avoid the nervous bundles as well, nervovascular bundles as well, to have as much as possible away from it. So these are the constraints we are working with. And usually the seed plans that we receive, assuming it was a straight needle, it looks something like that. So the algorithm required to minimize the patient trauma by minimizing the needle movements and the number of insertions using an oblique insertion. And also, we are aiming to allow for a seed placement accuracy of 1 millimeter. So we have achieved this by criticizing the geometric search space and choosing the needle path to maximize the number of seeds reachable for each needle trajectory. And we developed tests that show that the single insertion and 5 different cannula trajectories, the seeds can be placed in their planned operations. And the algorithm usually takes 6 to 9 seconds to plan the trajectory. So in this picture here, you can see the two options, the traditional one, the classical one, which is straight needles, and using the one at the bottom is the innovation from CoBra project, which is the needle is actually with a curvature, and we are trying with the seed plan to reach the main targets as originally planned, assuming that it was multiple needles that are straight. So this is the optimization is really built on that assumption. So we developed obviously the model on the contours from the finite element analysis, and we did simulation using MATLAB and C++. And one of the most important assumptions, as I said, is that it's to receive the plan previously prepared. Assuming that it was a straight needle. Our algorithm has proven to be quite efficient in terms of reaching these targets by generating different options and then optimizing by obviously trying to reach all the targets in the minimum time and with minimum number of insertions. Take, for example, one of the organs that is, I don't know if it's seen here, but you can see the straight line, vertical line, which is simulate the urethra, and we are trying to avoid it, and then and how to reach the target using the steerable needle. So we gave weight to the importance in discussion with urologist at Portsmouth Hospital University. The importance of the tissue damage inside the prostate, we give it a certain weight, and the tissue damage outside the prostate. And based on this assumption, we embedded this in the algorithm so that we can minimize the weighted tissue damage as much as possible using the different scenarios from the using this algorithm. And here, I mean, as I said, you can see the simulations and showing the multiple seeds going through the insertion. Really, the new algorithm acts for penetrating the prostate, caused movements and deformation, after which the correction mechanism is required, and the stylet should be pushed out when the cannula is inside the prostate to maintain the correction mechanism. So this would be the normal seed, and obviously with the inclination, it becomes a bit more complicated, but I mean, this is how our algorithm tend to work. Okay, so again, here are different scenarios, the variations of the trajectory algorithm that has been generated using our method, and how it can reach the different parts. And this is the user interface where it can show the different parameters in terms of the number of branches, number of trees, and the decision on how to build the effective trees from the insertion points as a visualization tool. So the optimal, it's really a multi-objective sort of optimum problem, where we are looking at the seed plan, and the optimal trajectory, or multiple trajectories. So obviously, in this case, we prefer as minimum number of insertions to the body as we can, as we can do. So the potential advantages of the CoBra project is that the nerve damage caused by needle and the neurovascular bundles in the normal brachytherapy, usually 50% of the patients suffer from erectile from ED. So we are assuming that with our method, that this would be rectified, because obviously we are trying to avoid any damage to the neurovascular bundles. Also, another important impact of our approach through from the CoBra project is that it can maximize the number of eligible patients. So we are not constrained by the size of the prostate, as Martin was mentioning as well, because it gives the surgeon more flexibility to reach parts from the prostate, which otherwise cannot be reached using the normal brachytherapy method. So as a conclusion, the software algorithm is currently being integrated with the rest of the modules in the project, with the University of Lille and other partners. And we start to do initial experiments, but this is still ongoing, and we will validate our approach. We think that further research can be done in possibly using machine learning or deep learning to optimize the weights, because we give some weights that can help our optimization based on the judgment of some clinicians, but maybe this can be done in a more automated way in the future, with an element of learning to the whole process as well. So this is really, in a nutshell, what has been developed. Thank you.
Many thanks, Ashraf. I have a quick question, if I may. How much time does it take to compute one scenario? I mean, you want to optimize possible scenarios. How much time does it take to compute this?
I recall, and Dylan can correct me if I'm wrong, I think I think 6 seconds usually was mentioned by Sina, between 6 to 9 seconds.
Okay. Yeah, that's clear. So that doesn't impact the regular clinical workflow by including this.
Oh, no. It's quite fast. Yeah.
Okay, great. Thank you. Any questions from the audience, other people? No, not at the moment. Okay, then thank you again.
Thank you.
We will now move on to presentation taken care of by Helene Kalkoen. She's from the company Demcon, and she will discuss the development of a biopsy module.
Yes, thank you, John, for the introduction. Yes, as explained, I'm from Demcon. We were responsible for development of the biopsy module. So the biopsy module is a module that will be added to the robot that's developed by Lille to be able to automatically perform a biopsy. So here's an overview of the system like we designed it. So to start, we have a rotational actuator for steering adjustments. So we did a lot of digging to see what the degrees of freedom were that we needed. And we found that there might be some bending of the needle after insertion, and you would like to be able to adjust that. And that's why we introduced a rotational actuator to be able to adjust the needle a little bit. Then we have a custom pneumatic cylinder that's responsible for the actuation of the firing mechanism to fire the biopsy needle. So the biopsy needle consists of cannula and stillet. I think it's the classic type of biopsy needle that we use here, and it's all integrated in a firing mechanism. And one of the things we focused on is the speed of the firing mechanism, because it's really important reaching a good quality biopsy. And of course, we made sure that the interface with the robot of Leo University was integrated properly. One of the challenges here was making sure all the materials would be MRI compatible. Yeah, we think we managed quite well here. So this is a further overview of the design with all components that shows a bit more of the inside of the mechanism. So the main mechanism is basically the firing of the needle that happens in 2 steps. So first the stillet. First the needle is inserted, the device is then loaded, then the stillet is fired, and right after the cannula is fired. So we decided to use an ultrasonic motor because it proved to be quite good for use in MRI. Only very limited distortion of their MRI signal. So that's why we selected this option. The pneumatic cylinder, of course, is even less causes even less distortion. So we developed a custom cylinder together with Festo that would fulfill the requirements that we needed, because the standard pneumatic cylinder, of course, is usually magnetic. So we had them updated to remove all magnetic components, so it would be suitable for use in MRI. Also the bearing, we used a ceramic bearing to make it also suitable. And then the other parts we have a spring in the system. Also, therefore, we selected the material that would be the best option, and that also holds for the other components. You see, so it all resulted in a prototype that you can see in this image, and we did some tests with our prototype in an MRI to verify whether it actually didn't distort the signal of the MRI, and whether everything was working properly inside the MRI, because of course you can distort the image, but the MRI itself can also distort the signaling of the system. So that's what we wanted to verify in our MRI test. So we went to the University of Twente for that and tested in a 1.5 Tesla MRI scanner. Unfortunately, we didn't have access to a 3 Tesla MRI scanner, so that was a slight limitation of this experiment. So we had a phantom and a biopsy module, and we put it inside the scanner, and we did some testing. So here are some images that show some of the results, and as you can see, in this image over here, there are only very limited artifacts from the needle itself. Also the dots you can see over here, and there wasn't any distortion visible on the normal use of the system. So we didn't see any artifacts or distortions from the materials. Also the encoder signals were fine in both the static and the active MRI field. We had no problems with the motor actuation either. Only if we actively moved the motor, we saw a little bit of noise in the MRI image. And then only very limited artifacts from the biopsy needle. I think you can never really exclude any artifacts in the biopsy needle, so we thought it was quite good. Last year we handed over our biopsy module to the University of Lille for further integration. So that's it.
Thank you, Helena. Any questions for Helena? I assume that everything was very clear. Thank you very much. Let's move on to Kevin Brubeni. He will discuss a very important topic, real-time dose calculation. Without that, we cannot have a good clinical outcome. So the floor is yours, Kevin.
Thank you. You are seeing my screen, right?
Yeah.
Okay, thank you. Hi everyone, I'm Kevin Bonny and I will present the work of my PhD thesis focused on the dose calculation of MRI. But first, a brief explanation of brachytherapy. Brachytherapy is a therapy primarily intended for the treatment of less aggressive tumor. It is internal rejection and less harmful alternative. In this therapy, the rays are effective at short distance from within the body. The big advantage is the prostate can be treated fairly accurately. This also results in the least possible harm to healthy tissue. You can see on the picture the area between the scrotum and the anus. A needle is used to place radioactive seed in the prostate gland. This treatment is performed under anesthesia. The seeds are not removed after the treatment, but are permanently left in the prostate. This is called low dose rate, opposed to high dose rate, in which the number of catheter thin tube are inserted in the prostate for radiation fluid to pass through. The fluid and catheter are removed after treatment to ensure no foreign and radioactive material remain in the body. The treatment required the acquisition of the patient geometry by using a pre-treatment CT. A patient acquisition is made after the insertion of the catheter, thus taking into account in some extent the deformation of the prostate. The voxels are expressed in Hounsfield units, directly correlated to the electron density needed to compute the dose deposit in the medium. In CoBra, we use an MRI to simulate the patient geometry. It offers better contrast and avoid extra irradiation, meaning that we can update in real time the patient geometry and update the treatment planning on the fly. The first problem on the MR-guided brachytherapy is the use of compatible device. This is the work of other CoBra partner. Basically, no one cannot use solely the voxel intensity of the MR to compute a dose distribution. This is the first problem, and those calculations can be performed directly on the MR image since no correlation has been demonstrated between the nuclear magnetic property on which MRI depends and the electron density, which is the property used to model radiation attenuation in humans. The proposed solution is to generate a synthetic CT from the MRI using a deep learning model. Deep learning solutions are usually accurate and offer a decrease in computation time. This is not a new topic and in the literature, but the CoBra requirements have added new challenges. Current practices use bulk density, in which we reassign manually MRI intensity into a set of various bins of Hounsfield units. This is a major step back considering the use of MRI. In terms of image generation, generative adversarial network GAN work extremely well. Generate a synthetic CT in image processing. It is in image processing an image-to-image translation problem. To be solved, we begin first with a database of MRI and CT. We then train the GAN to convert an MRI into a CT. Then we assess our trained model. We generate a SCT from a test set and compare it to a reference CT. The first assessment is a global image comparison, voxel-wise. We then go further with a dose comparison also. We made a proof of concept using a conditional GAN with multi-center data. It is not a new method. Several studies try to improve their accuracy. In accordance with CoBra, we aim to generalize this type of method with different MR constructor or sequence. We investigate these two methods. The first one with paired data, in which we use a non-rigid registration between the MR and the CT, and unpaired data in which we just use rigid registration. Data prep, the second method is quite useful because data pre-processing by doing the non-rigid registration is quite time consuming And the use of non-rigid deformation is subject of debate among the community. That is why we choose to work with unpaired data and select another GAN model you call cycle GAN. The major contribution in the study is the improvement of generalization issue in deep learning. So far, no one has been able to generate synthetic CT with multi-center data. We have been using the image coming from 3 sites with 6 different scanners. The improvement it is in accordance with our need. Indeed, an optimization of MRS sequence in order to see the catheter has been carried out during my thesis, meaning that it was impossible to build a proper database and train the model. The use of multi-center data induce MRI variability in the model, allowing us to generate a synthetic CT from unseen MRI. Here you can see the real CT and the SCT in which we compute the dose distribution and the difference. Mean relative difference in dose to the prescription is always above 1%, meaning that clinically it's perfectly relevant. The second study using the cycle GAN, this time we use non-paired data, but with more testing patients. Oh. There is a problem. You don't see my screen?
We do see your screen.
Okay.
Yeah, it's working.
I've been disconnected. Sorry.
Yeah, it's on again.
Okay.
The presentation is stalled, I guess.
What?
Your presentation doesn't seem to move forward. I think that's the problem.
Oh, I will. Okay, good.
So maybe you can wrap up with your conclusions.
Yes, I think so. It is working now?
We see the same image. Yes, it's moving forward. Thank you.
Okay. I will go fast. Secondly, even if we obtain the electron density, compute an accurate dose distribution in matter of seconds is quite impossible. Current practice use the TG43 formalisms, which assume that a patient body is an infinite water phantom with uniform density. The influence of the tissue and applicator heterogeneity, entered source attenuation, and infinite patient dimension is ignored. That's why once again, we're looking for a deep learning solution to predict a Monte Carlo dose distribution, which is the gold standard in terms of accuracy. Compared to the synthetic CT, we use a convolutional neural net to predict the dose. First, we need to know exactly the input needed to perform the dose prediction. First, the MR is by converting it into a synthetic CT, give us the information related to the electron density. Second, a treatment plan in DICOM format in which we extract the 3D position of the source into a 3D matrix called here a soft treatment plan. And finally, we align this to volume for ease of use. Even if deep learning for inference is fast, 3D is still a challenge. This is why we encode the synthetic CT using feature-wise linear modulation. It allows to condition information by extracting in the synthetic CT. Only important feature need to translate the soft treatment plan into a dose distribution. We do not have sufficient Monte Carlo data for training. Therefore, we replace it with those computed on the treatment planning system, This step is known as transfer learning. I will stop there, I think, and thank you all for your attention.
Thank you, Kevin. Sorry, I had to ask you to speed up a bit, but we're on a tight schedule. Very nice development, very important. New technologies in improving dose calculation. Considering the time, I would like to move on. Again, giving the floor to Rushdie to now share the entire integrated solution. Rushdie, feel free to share your slides. Or am I looking at the wrong schedule? No. No, I'm good. You're muted, Rushdie.
Sorry. Everyone hear me now? Do you hear me?
Yes, we can hear you.
Good, excellent, thank you. So I represent all the authors or the main authors for all this development or integration, because actually they are busy for the preparation of the demonstration. So I will share this slide for them. Rapid positioning comparing to the clinical workflow for the MR robotized biopsy that we approved it with the with our clinical partners. The aim here is to divide the workflow on 3 phases, regrouping the pre-treatment, the diagnosis phase, and the post-treatment. So our main focus is in the pre-treatment and the diagnosis phase, where here we can see all the blocks and the interaction between the input and the output of each blocks, and the implication of the partners to prepare all the anatomic assessment, allowing to plan the trajectory of the robot to guide the specific mini-invasive needle, even steerable or rigid one, with the cooperation of all the partners that have already introduced their contributions. And for the online diagnosis here, we are in MR environment, and the aim here, we have to find all the options and the functionalities to switch from a full execution plan to, for example, exceptional handling one or teleoperating mode, if necessary, if the target is relatively moving. And we have the post-treatment phase, where we want to make the reporting and the maintenance and storage, of course. Concerning the brachytherapy process or the workflow, the same, we divide it in three main phases, where here we have to consider, between the anatomic assessment and the robot planning, the dosimetric planning, and this dosimetric planning allow us, of course, to generate automatically the trajectories of the needles to track the main target in the prostate organ, and then to interface after with the MR images to make an adaptive tracking if the target is moving on in real time. Here we have this work has been done by using facilities coming from our partner observers, like the seed loaders, like the planning software, and also the MRI facilities. Coming back to the robot guide. What we speak here about robot guide is the structure of the robot, which can support or hold even the biopsy module or the brachytherapy module. Okay, so before starting designing it, we did strong work thanks to CEPAL and all the co-authors of this contribution, where we did the comparative work about the existing solution nowadays, which is AMR compatible robot intervention for brachytherapy in terms of kinematic structure, if it's serial or parallel, and their compatibility to different type of MRI machine, 3 Tesla, 1.5 Tesla. When I say this, the compatibility in terms of actuations, in terms of sensors or embedded sensors, and also the accuracy and the repeatabilities. So here we can have a global comparison here from this table, and in general, if we can make one and the main positioning of CoBra solution comparing to what it exists as a solution right nowadays is the ability to make this intervention on board in real condition without any interruption of the MR machine to make almost acquisition. That means the solution that we proposed here through CoBra project is compatible with 3 Tesla MR machine and without any disturbances of the images. This is our main concept. If we go to the this robot guide, you can see here in the picture, it is a parallel kinematic robot with the 5 degrees of freedom, composed with the prismatic, rotative actuations, and the actuations here is ultrasonic one, like the module of the biopsy explained before by the income, and this can support what you can say different the 2 types of modules, even for the brachytherapy or for the biopsy. Yeah, having this collaborative work, yeah. Of course, I have to insist on the fact that such structure or such kinematic has not been developed only from the side of the roboticians, but with the strong work or collaboration with the clinical partners, where all the specification has been just to give a simple example. For example, knowing the position, the placement of the patient inside the or in board the MR, right? Yeah, we took more than 1 year to decide in which optimal position we should place the patient. That we and finally we go from the lithotomy. It's for that all this information is important to identify which kinematic we have to consider and to develop the workspace necessary for the robot. Here we can see the lithotomy position for the patient and the placement of the robot guide. Of course, here to stabilize the legs of the patient, we used a facility provided by NORAS, our observer partner, which is Unilift. Yeah, that we can stabilize the target, and then we can calibrate the robot according to this one. Head, yeah, here in terms of yeah, it's more technical one, but the aim here is we need, after designing the robot, to model it in order to improve the control of this later, even from speed part or position part. Some tests done in MR conditions in closed loop to see the performance of the tracking in terms of position and velocity. Position at the joint, at the joint part, and here at the task part. Yes, my colleague Mario will introduce you in details all this part, but the first test of the robot guide with the different modules has been tested on what we call it here active phantom, that we tried to develop a concept of phantom where we can introduce disturbances that we can have in real conditions like the inflammation and the deformation of the tissue in contact with the needle. Yeah, this work. Here for the tracking of the system, this is our internal GPS to track the markers placed here on the phantoms. Yeah, we see this more in details during the demonstration part. And finally, the coming development on live animals biopsy will be the integration of all the path planning generation that Ashraf from University of Pasteur introduced it to you before during the coming tests, and also how we can guide also for rigid needles, how we can use also a specific template guide with the minimum entry points. And finally, we want to test in real condition the adaptive brachytherapy tracking when the prostate is moving during the contact with the tissues. Thank you so much for your attention. Thank you, John.
Thank you, Roshi. Yes, of course, an important step is the validation of the system with animal studies being planned, but part of the validation is also the development of a prostate phantom. And Mario will now share, and this is the last presentation before we move to the demonstration, the development of an active prostate phantom.
Exactly. Can you hear me, everyone?
Yeah.
So let's sorry. Yes, that's it. Okay, so thank you everyone for being here, and I'm going to talk to you about this bio-inspired phantom, which is a tool for us to validate all the workflow that you've been introduced to. And so I'm going to talk a little bit about what it is, why we have to make it, how we need to make it, and how it works, and a couple of results. So this is pretty much the first view of the bio-inspired phantom, in which you can see here we just used a rod to move it around, but it represents the needle, and it's attached to a frame to pretty much simulate the ligaments and all the the structures around the prostate, but compressing it, condensating rather. And so what we want to do is something which is the goal of a phantom that mimics the actual organ, and particularly specialized in the dynamic behavior or the motion of the organ during intervention. The fact of replacing ultrasound imaging and taking out the rectal probe and other sustaining structures to the prostate makes it more mobile and so prone to deformations and displacements that so far we don't take it into account, since there is no real-time images of what is going on during an actual intervention. So we use the SOFA framework as the software to calculate all those deformations. And we also take into account, or rather mimic, inflammation of the prostate itself with a cavity, a pneumatic cavity that is inside the prostate. You will get more details afterwards. And yeah, it's pretty much necessary to validate the medical devices before testing on human or even animals, and most likely it will help getting certification processes more quickly. So just a quick view about the previous work and what's on the market. Usually for this kind of interventions, we use static phantoms, which are made for having good imagery or good image quality with respect to the real organ, and but they are all static, and there is no way it can move or represent the motion or the scene migration or even inflammation, except some laboratory research that can take into account partially. So now we're getting into the hole that is in the market. So that's what we want to fill. So the specifications for our concept was to have something that could be able to validate the CoBra concept both for the patient and for the robot. So it needs to represent the lithotomy position and be able to move displacement, pitch and yaw, and if possible, inflammation. So the concept that has been developed is depicted here. So you get the bulb of the prostate with the inner cavity, which has been placed in the place of the urethra, so that we're sure that it will never be pierced, just like in the regular intervention, and it's surrounded by or held by 4 arms, which have pneumatic cavities to which there are tubing attached, and from which we measure the changes of pressure. And with this information, we can reconstruct the prostate, well, the phantom configuration. So I'm going to show you just a video about the concept. So this has been submitted last year, and it's an overview of the phantom seen also as a regular human-machine interface, as you can actively interact with it. This is just real-time data of needle insertion, and but we can use it as an interaction device. So in the next cut, you will see it, and yeah, it moves around. You can see the pressure variations, and the fact that it can move in real time, and simulation, it's quite accurate. We made a measurement. That is the reason why you can see those markers here, and you will see the results. Here you can see how we can apply pressure to the inner cavity, and it inflates slightly, and it doesn't affect the overall interaction with it. So you can still move it around while emulating edema. So let's sorry, yes. Back to our business. So how it has been made? It's with silicon. This particular first model was made with Ecoflex silicon, but we made another one with gel, and that is rather representative in both in shape, size, and hardness to an actual prostate. And it's been casted in halves, just keeping the cavities. And there are pressure sensors that can measure down to 11 pascals of pressure variation, which is quite useful when you have around 12 meters of tubing between the small cavity and the sensor. And it's all converted with just an Arduino to a host computer. So this is the main workflow, and there is a digital twin. So in the simulation, 3D model of the same phantom computed in with finite element model that allows to have the mechanical properties of the phantom, and quadratic programming minimization technique to solve the problem. So about the I'm not going to get into the details of the equations. So it's just a reconstruction of the supposed pressure that is being applied with respect to the pressures, and those are measurements on the tracking, which looks quite accurate, and it actually is. And we're this is what I was talking about, of having a second iteration with a shell and an infill with silicon gel. So about MRI, I'm going to get back to share just this quick. This is data gathered on real-time MRI during needle insertion. So for those who have been there, it vibrates a little bit. That's why it's moving. And you're going to see by the end of the video how, yeah, that's a needle insertion. And you can clearly see the moment it happens. There are, I think the video that will be shared afterwards will show side by side with the actual insertion, the acquisition that was made. So that's all from my side. Thank you for your attention. If you have questions.
Thank you, Mario. It's a very nice development, a very important one as well. Not only for this development within CoBra, but I'm quite sure that this model can also be used to validate other setups, new needle devices, and so on. So thank you again. As I assume that it's possible for people to ask questions during the demonstration, I propose that we now move forward to the demonstration of the system. I'm not sure whether you still have to set up some...
Yes. So indeed, we can, excuse me, let's get to Teams, because there is another
Great.
So, welcome to the CoBra room, where you can see real time. Here you got Bernardo inside the MRI and the robot. So let's move it a bit backwards so you can see the concept itself. Here's the robot. I mounted the biopsy module. Yeah. So yeah. So those are, this is the biopsy module. Yes. You can yeah, most probably see the laser. And so we mounted a target, which is a grid that can be seen with in the MRI camera that is here. Okay, so and the robot that has the needle already inserted in the entrance of this point. So this grid is just for us to have reference points so that we can cover the maximum data set, the maximum workspace. And what I'm going to do now is teleoperate, which is what you see on the left right bottom part. This is the teleoperation interface in which you can move around. The red arrow is the position of the robot itself. And once you get to the position of the robot, you can define as the insertion point At this stage, yes. So it's grabbing. I just wanted to make sure that the MR camera was moving. We can advance, and you can see the robot moving very slowly, actually slow enough to be barely seen on the images. So once we got inserted, we can move around. You can see now I'm just turning, and it turns with respect to the entry point, so that we can respect the motion of the robot itself. So I'm going to move it a little to the right, and you're going to see it turning slowly. Yes. Something wrong. Yes. Yeah, so I got the entry point wrong. I guess there is some shift there. So whenever I want to perform a biopsy, there is an action button that allows me to do so. Seems like there is some problem with the system. Now I'm about to fire in the air, obviously, because you won't be able to see, but fire the biopsy module. And that is a moment where we can get the sample. Sorry, I'm going to do it again because the image froze. So well, it's still frozen. And at this point, we can gather the sample analysis. And so the you can barely see from this camera. This is the point where take out, you know, the sample and take it to the lab.
Thank you, Mario, for this first scenario of tests with the for the attendees, it is interesting to see all the concepts. Here we have the mannequin of in lithotomy position, where the legs are stabilized with the unilift module, and we are using a camera, indoor camera of MR, provided by one of our partner observer called MRC. We can see the robot guide here inside with the 5 degrees of freedom, actually, which hold the module, the biopsy module of DEMCOM. There is 2 types of actuations here for the module. One pneumatic, what you are seeing the cables here for the attraction of the tissue, and one for rotating the needle, where the other for the rest of the actuator are all piezoelectric one. Okay, so this is first of all, to calibrate the robot, we need to first place the patient to stabilize the legs, and then the robots can calibrate the patient, and then we have a program of calibration of the robot according to the static position of the legs, which are attached to the frame of the unilift. Now, for this application, we are using, if you see here, the grid. In order to be this grid is used with a minimum entry point for 2 objectives. One, to minimize the inflection of the needle, during the insertion, and the second objective also of this one, it's our second guide, because this will be in touch directly with the perineal part of the patient, and we are emulating here. We are emulating the the prostate, one prostate layer, for example, plan with such specific phantom grid, if I can say, where if you can we placed it here in homogeneous grid, where some markers are placed inside. These markers are biomarkers, one proposed by one of our partner observer called Nanovi, and these markers are also used to emulate lesions that we want to track and detectable, easy detectable in MR with high field. Yes, globally here is the environment of the biopsy concept inside the MR. Of course, in our lab, we have a scan here, but is mock-up. It's not. We don't have the magnet here because we are in the lab. At the hospital, when we test it, all the equipment that you have here are compatible to 3 Tesla, and we are all the electronics are isolated to avoid any disturbances inside. Okay, so to switch to the second scenario for the brachytherapy, Sepal will introduce you a short film that explains the principle, and in parallel we are preparing this scenario for you.
Hello, I'm audible. I will try to give a small recap about the CoBra story, that how we progressed and being it is a collaborator project. So how the partners helped in different modules and how we integrated the different components to make it as a functional robotic device for the prostate cancer cure. So from this, we can see the 5 degree of parallel kinematic robot can perform inside the MRI with the patient in the lithotomy position, making it convenient and stable for the patient. Same time, enough workspace for robot to operate inside. Now, the second part is that we require some sort of phantom which can emulate like the real prostate organ, so to test the motion while performing the needle intervention. Now this phantom will be used for the physician's training to use the robot. And the next step, we have added the emulation of edema inside so that we can take care of the swelling for the tracking of the target shift inside. Next part comes are the brachytherapy. This is the automated implant driver equipped with the 2 ultrasonic motors to navigate the seed through the flexible catheter with the help of the MR safe guide wire to push the seed up to the needle tip. Here we demonstrate the CoBra robot's capability to perform the oblique insertions with an objective to make minimal entry points, as we were demonstrating in the live video. So this makes it a potential with one single entry point to cover the multiple target regions inside the prostate. Now this is the real-time MRI scenario where we tested the needle intervention on the phantom. Next, it comes with for the accurate, precise targeting to reach the targets in the occult region. The TU Delft, in collaboration, developed the steerable needle concept. So here you can see the difference between the conventional as well as the steerable needle reachability. As Martijn explained, this is equipped with the steering mechanism, which can reach with the curve to next steps. The University of Portsmouth developed a trajectory planning algorithm, so which help us to make the trajectory planning to minimize the trauma and covering the whole prostate with a single entry point. Here comes the part which the Mario tried to demonstrate through the live video, so that this is the potential of our robotic concept. We can target multiple points with a single entry mechanism, and it helps to reduce the tissue damage and trauma to the patient. Now comes the inboard scenario and the components involved for the whole setup. So this the absolute encoders, like a form of sensor, are assisted by the numeric GINA, MR guide by the Marvis, catheter by the JUICE, MIC applicator by the BBIG, biomarkers by the Nonovi, and Unilift by the NORAS, along with the MR safe camera. So these are the recent experiment tests performed at the Philips Center. So we really got precise targeting results and the left below corner represents the intervention zone, the slice of the targets. So we try to hit target markers as well as the open areas to see the needle tip artifacts. Next comes with the collaboration, the DAMCON, the biopsy module. Here we perform the biopsy on the bio-inspired prostate phantom. And after those all successful tests, we performed the biopsy on the dog cadaver, and OCR helped us to facilitate the veterinary specialists as well as the dog cadaver to extract the this biopsy core on the prostate. So from the video, you can see the robot performing the biopsy fire and the successful extraction of the needle after performing the biopsy fire. Thanks, and please share your questions if you.
Okay. Thank you, Chapal, for again giving this good overview. Obviously, there are always technical challenges in giving a good demonstration, especially when it's being done online. But hopefully the audience got a good impression of the status of the system, where it's now, how far it is in terms of validation and testing. Are there any questions that could be addressed right now?
I have a small question for Chapal. I haven't seen the video you just showed, so it's really interesting to see. Was it scanned by the MRI real time, or was the dog placed outside the MR bore for performing the biopsy?
The dog cadaver tests were performed outside because these were the very first tests. So we had a meeting with the veterinaries, so how we can use this robot and teleoperate it. So they used this robot with the teleoperation module to reach the planned target inside the dead dog. So these tests were not inside, but as they were the first tests, and we have to take ethical permissions to perform tests on the dogs. So they were performed on the dead dog. So our next plans are to perform these tests on the dog cadaver inside the MR room.
Okay. Thank you.
Thank you for your question.
We come back to the for the brachytherapy process here. We want to show you first the module of implant deposit, what you can see here on the screen on the top right side. The top right side, you have here a mechanism where we have here the loader of the seats, LDR seats here, proposed our it's big loader, and you have here two types of actuations. One is used to pilot or to drive this mandarin, which push the implant, placed here in vertically, and we have here detectors, position detectors of the implant. According to that, we run another we drive another motor allows to drive this catheter. This catheter is Marvis catheter, MR compatible to drive along this trajectory the implant until the tip of the needle, which is located inside the prostate at the accurate location. So here we are not using the steerable needle. First, we are using this conventional rigid one. The principle here is to show you how this implant module is run automatically. Mario, is if you can start driving this, and I let you.
Thank you, Professor.
Thank you.
So the principle, I'm going to first mimic loading of a seed. Just disclosure, we lifted the mic charger because you won't be able to see the small grains, the small seeds. So what happens to see more clearly, you have in the upper right of your screen a close-up of how this is going to work. So you can see that now I'm charging. And once it's charged, the seed is roughly, the spot where Professor is pointing at. Then we pull back. And we can start pushing the wire guide. And it will go, it will guide the seed all along the tubing. Up to the target. And so once we loaded, we pull back and get back to the starting point and load the next charger, the next seed, sorry. And last but not least, I installed the bio-inspired Phantom. So right now, you can barely see it, but the needle is inserted beyond the membrane that sorry. Okay. It's inconvenient. Yeah, sorry, that was technical issues. So you can see that the needle is inserted beyond the membrane that we use as the perineum skin threshold, and it's almost touching the prostate. And on the right window, you can see the simulation running of the prostate with roughly the same point of view. So now I'm going to insert the needle, and you're going to see the simulation reacting to it. Now you got in contact, so you can see the arrow that is growing. This is the representation of the forces. So the more we press into it, the more it deforms. And I'm going to pull back a little bit just to show you. This is not what happens in an actual intervention, but just for yes, for visualization, I'm moving upwards and sideways. And once we're out, we're mostly out. Yeah, okay, sorry. So
It's a camera lag.
yeah. So yeah, now I'm moving the needle slightly leftwards, so that you can see that there is also another dimension of motion. And we can also move it slightly backwards. This feature will help us assess the stability of the whole needle insertion process and the seed loading. And now we're out. So this simulation has been proven to be accurate enough, and will help us in the near future to steer accurately the needle and perform tests beyond the MRI environment, which will hopefully speed up the whole process of the robot evolution.
Yeah, thank you, Mario. So the next step, by April 1st, we will realize our first extraction of tissues on dead animals, but in real MR conditions at the hospital. With this, yeah, the aim is to optimize the time of the calibration of all the process, and to extract this. The future test will help us to prepare the on-live intervention by the end of May or beginning of June. And this work will be realized in partnership with OCR and veterinary doctors, where the objective is to test the repeatability, accuracy of the robot insertion and to test all the components separately. Yeah, as you know, actually in our lab, our main feedback of images are coming from the simulation part, but not from real images. So this is what we want to. It's the first step before final implementation. So what we want to show today is the overall integration of the bricks developed by all the partners around a common concept that we want to test it now progressively from the according to the future test to resolve and to perform the specification of such robot according to the needs of the end users. So thank you so much, and first I want to thank Mario, Sipal, Fabrikator Otman, who are not present today, and Cecile for their strong preparation of this demonstration. It's not easy to do it usually on online to perform in a short time all the tests and to check all the parts of the components, and hope this show can help the attendees to understand the overall concept of CoBra, and we are happy to answer to your questions if it exists. Thank you so much, John, and thank you for all.
Thank you, Roshdi. Yeah, there's still some time for questions, but before I'll give people the room for that, I want to emphasize that, well, again, we are quite happy that we were able to organize this demonstration at least online. But a final event of the project is organized in Lille on 21st of June, but also a physical demonstration will take place in the ASTRO conference in Copenhagen, which is organized the 6th up to the 10th of May. So people attending that conference have the opportunity to see the setup from close by. And as you can imagine, it's easier to get an insight in the exact working of the device when you're standing next to it than via a camera like now. Thank you again for the demonstration. Are there questions from the audience? Okay, I don't see any questions right now. Well, as said, the videos will be placed online, which gives you the opportunity to have a closer look at some of the talks and some of the demos. Also to rewind them once in a while if things went too fast or too slow. Yeah, for now I can only thank you again for your attendance, and hope to see you in Lille in June, or in Copenhagen at ASTRO. And Maximilian is sharing via the chat the link to the conference, I guess, right? I have to check what's being shared right now. Oh, the attendants will receive an email with additional information about these events. Okay. Well, thank you very much. Still right in between the scheduled time of 4 o'clock. Hope to see you soon live. And for now, I wish you a very good day. Thank you. Thank you all.
Thank you. Bye.
Thank you all. Thank you.